Hello everyone, welcome back to Introduction to Logic. This week we're going to continue our unit on natural deduction. We're going to learn a few more proof rules this week. Some of them are going to be fairly more complicated than the ones we learned last week. So try to stay with me and pause the video as you need to work the examples yourself. Okay? All right, let's get started. So we're going to learn 7 new rules this week. Sounds challenging. It will be, but you can handle it. First up, we're going to learn something simple: biconditional elimination. Biconditional elimination works exactly like conditional elimination, except you can use both sides. Okay? So remember, conditional elimination looked like this. If you knew a conditional is true, and you know the left side of it's true, you can derive the right side. Okay? Conditional elimination allows you to solve, very simply, a problem like that one. Biconditional elimination does the same thing, but in both directions. So let's say you have a biconditional like this: P if and only if Q. Well, if you knew on another premise or another line that Q was true, this time you could derive P. You can't do that with conditional elimination, right? That's an invalid inference. Let's see how it works in our formal proof structure here. We put our premises above the horizontal line. So P if and only if Q, and Q. 1, 2. On line 3, we can derive P. We cite biconditional elimination. And we're going to cite first the line that has the biconditional on it, and then next the line that has either the left or the right side of the biconditional we're using. So that's 2. Okay, pretty simple. It works just like conditional elimination, except you're allowed to use the right side to unlock the left side, and the left side to unlock the right side. All right, let's move on to biconditional introduction. This one is a bit trickier because it involves subproof, specifically multiple subproof, right? So that can always trip students up when they say that they're going to have to use more than one. Let's say you had the following: if P then R, and if R then P. Well, you can see that these two things share in a very intimate relationship, right? You will be able to prove that P if and only if R, in fact. But how? How do we go about doing that? Well, let's learn by example here. First up, set up our argument the same way as always, get our premises down. If P then R, and if R then P, 1 and 2. You're going to begin a biconditional introduction proof by assuming the left side of the biconditional. The goal after assuming the left side is to produce the right side of that biconditional. So I'm going to assume P in hopes that I can get to R. And I can do that pretty easily. Right? That's just conditional elimination from line 1 and 3. Okay? Second, I'm going to create a space between that assumption and introduce a new subproof. So this new subproof is not under the subproof that starts on 3. It's entirely separate. It's parallel. Okay? This time, I'm going to assume the right side of the biconditional I'm trying to produce and hope to arrive at the left side. So I'm going to assume R. And try to arrive at P. Can I do that? Yeah. I can do that using the same exact move, conditional elimination. This time it's line 2 and 5. Great. Now that I've accomplished those tasks, I can lay claim to P if and only if R. And that's going to be biconditional introduction. and I need to cite both subproofs. So that's 3 through 4, 5 through 6. Okay, so it's not that tricky. It's just a little different because we are working with 2 different subproofs here. It's a bit unique in that sense. Okay, now we can do another just for practice's sake, since this 2 new subproof thing should be new to you. Suppose you have the following argument: A and B, then C, C, then A and B, and D. And you want to arrive at the following: A and B, if and only if C. Okay, so let's start the same way as always. We need our lines so we can get our premises down. Premise 1, if A and B, then C. Premise 2, C, then A and B, and D. 1, 2. So again, we're going to start by assuming the left side of the biconditional we're trying to introduce. So I'm going to assume A and B. Having assumed A and B, I want to get to the right side of the biconditional I'm trying to introduce. Can I do that? Yes. I can get C using conditional elimination 1, 3. Okay. Now I can move on to my second subproof. On line 5, I want to start by assuming the right side of the biconditional here. So I'm going to assume C and try to produce the left side, A and B. Now, C can get me something close here, right? I can get A and B and D with conditional elimination 2, 5. Okay, but that's not quite A and B. That's A and B and D. So we need to get rid of the D. And we can do that pretty simply. A and B, conjunction, elimination, 6. And now I can leave these subproofs. Let's say 8, A and B, if and only if C, biconditional introduction, 3 through 4, comma, 5 through 7. That's it. Okay. Let's move on. Let's start looking at disjunction rules. Let's start with a simple one. Disjunction introduction. Okay. Disjunction introduction, also known as addition in some other systems, works like this. If you know something, like P, or you've assumed something, you can derive that thing, P, plus, that's why it's called addition, a disjunction symbol, and anything else you want. Okay? So if you know P, you also know P or Q. Why? Well, because a disjunction is true if either side of the disjunction is true. So it's true if this is true, and it's true if this is true. And we already know that one side of it has to be true, or we've assumed that that's the case. The disjunction has to be true. This works because P or Q is technically a weaker claim than P is. So you're actually introducing a weaker claim. You're taking something that's pretty strong, right? I'm asserting that P is true and making it, well, P might be true, but it might be Q, right? So it's a weaker claim. Okay, so how do you go about showing this in like an argument? It's pretty simple. Start the same way as always. We have P as premise 1. Here we say P or Q we write disjunction introduction, and you simply cite the line that you're adding to. Okay? Now, a few things about disjunction introduction. Number one, you can add literally anything else you want, so long as it's accompanied with that disjunction. So from P, I could also get P or Q and R. Okay? It can be as complicated as you want it to be, so long as it's joined with that disjunction symbol. Okay? Second, you can use disjunction introduction on anything that you know or have assumed. So for example, I can go from if P then Q to if P then Q or R, using the exact same move, right? This is something I know or have assumed, okay? And I'm just adding a disjunction symbol plus anything else I want. So disjunction introduction is not intuitive for a lot of first-time logicians, but it's very useful. And once you get the hang of it, it's pretty easy. It only takes one step. We love that, right? Just one step. No assumptions. Okay. The next rule is not so easy. Disjunction elimination is indeed going to require assumptions. In fact, it's going to require two of them. We're going to use two subproofs again. Disjunction elimination allows us to actually make use of disjunctions. Most of the time, when you see a disjunction in a proof within natural deduction, it's slightly annoying because you can't really use it. If you see, for example, if P then Q, and you have P and R, well, that conjunction is very useful because I can break it apart and then use it to get Q, right? Using conditional elimination. But if instead I have a disjunction, well, that doesn't let me do anything, right? I don't know for sure whether I have P, so I don't know for sure whether I can get Q. So normally, disjunctions aren't a happy sight when you're working, trying to find any kind of insight that you can through natural deduction. However, there are some ways to make them useful if the right conditions can be met. So, for example, if you know that if A then C, and you know that if B then C, A or B could be quite useful if you're trying to derive C. And intuitively, you should be able to see why this is the case, right? A or B, that means A has to be true, or B has to be true, or both of them have to be true. And if that's the case, what happens? Well, then we're going to be able to use conditional elimination to get C, right? So we know C is going to be, it's going to be possible to derive C here. This is going to be a valid argument. But how do we prove it using our system? Well, let's start the same way as we always do. We need our lines. Okay. We put our premises down. If A, then C. If B, then C. And A or B. That's 1, 2, and 3. Okay. The way you use disjunction elimination is you begin by assuming the left side. We're assuming the left side of the disjunction, okay? Now, what's the point? Why are we assuming anything to begin with? In disjunction elimination, our goal is to assume the left side first, arrive at a result that we want. Let's say C, right? So I'm going to assume A and try to get to C. Then I'm going to assume B and also try to get to C and try to get to the same thing. If both of these things, these disjuncts, lead you to the same conclusion, you're allowed to draw that conclusion, okay? Because the disjunction says that one of those sides or both of them has to be true, okay? So it works like this. I've assumed the left side, that's A. Can I get to C? Absolutely. That's conditional elimination 1, 4. Great. I'm going to start a new subproof now. Just like by conditional introduction, this is a separate subproof. So there's going to be space between these vertical lines. Okay. Can I get from B to C? Yes, using the exact same move, just referring to different lines. 2, 6. Now I get to say C outside of any assumption but my premises. I'm going to cite disjunction, elimination. And here's the difference between this and biconditional elimination. I need to cite first the disjunction I'm getting rid of. That's on line 3. Then I'm going to cite the left side subproof. That's 4 through 5. And then the right side subproof, which is 6 through 7. Okay. Not too bad. You'll see a lot more of these as we practice today. So this won't be the last one you see. All right, let's move on. The rules get a little trickier from here. Let's start with negation elimination. Negation elimination basically just says that when you find two things that are contradictory, you can introduce a contradiction symbol. Okay, so it's going to look like this. Suppose you have the following: if P then Q, and P and not Q. Okay. We don't even need to talk about reaching a conclusion. Negation elimination is not a tool that you use to draw a conclusion. In fact, it can't derive any kind of conclusion. The only thing that it can produce is a contradiction symbol, right? Which is not a sentence, right? So in practice, it would look like this. If P then Q, P and not Q. That's 1 and 2. On line 3, I can get P by itself. That's and elimination 2. On line 4, I can get not Q by itself. That's and elimination 2. On line 5, I can get Q by itself from conditional elimination 1 and 3. Okay. Notice on lines 4 and 5, I have a contradiction. Q and not Q. That's what you're looking for with negation elimination. On line 6, I can then draw this symbol. This symbol means contradiction. Okay? So I'm entitled to draw this symbol because I have a thing and its negation. So this and this, that's a contradiction, right? Or this and this, that's a contradiction, right? So long as you have something and its negation, you have a contradiction. All right. Now I'm going to cite negation elimination. I'm going to cite 4, 5. That's it. That's all negation elimination is. It says, look, I found two contradictory lines, thus I'm entitled to draw the contradiction symbol. Okay? There's really nothing more to that. So we'll put this here just for reference. It's about producing contradictions. You'll soon see why that's useful. So now we can talk about negation introduction. Okay? This rule you're going to use a lot, right? This is a very important rule. It helps us solve many, many proofs that we would not otherwise be able to solve. For example, suppose you know the conditional if P then Q. Suppose further you know that Q is false. Well, it follows that P is false. This is called modus tollens. It's another valid elementary argument form. But how do we prove it? Well, in this system, at least right now, we're going to have to use negation introduction. It's going to look like this. If P, then Q, and not Q. 1, 2. For a negation introduction proof, you're going to start by assuming the opposite of your conclusion. So I'm going to start by assuming P. That's the opposite of what I'm trying to get, right? P and not P. Those are opposites. Now that I have P, I want to try and get a contradiction out of it. I'm looking to generate a contradiction here. That's my goal. Okay? So I can get Q from conditional elimination 1, 3. And once I have Q, I can get contradiction using negation elimination from lines 2 and 4. See, 2 and 4 are opposites, so that's a contradiction. Now that I have a contradiction, I'm allowed to say, oh, P must have been false. Negation introduction 3 through 5. Okay? And that's that. Now, why does this work? A contradiction is not allowed. Okay, so there are 3 laws of logic that cannot be violated. There's the law of identity, which is P is identical to P, right? Always. So if P is true, P is true. Okay, so if P, then P, P if and only if P, right? All these things are always true, no matter what. Okay, that's law of identity. There's also the law of excluded middle. So P has to be true or not P has to be true. Why? Because there's only true and false. You've either got to be true or you got to be false. One or the other. Okay? The last rule is the law of non-contradiction. It says it can never be the case that P and not P are true. You can only be one or the other. You can't be both. Okay? So, because a contradiction violates that rule, it's saying in this particular example that Q and not Q is true at the same time. The rule has been broken. We can't allow that. We have to bring the system back into balance, so to speak. And the only way to do that is to say that the assumption we made, P, which led us to that contradiction, had to be false. If it leads you to a contradiction, it has to be false. This argument form is very common in philosophical and perhaps legal reasoning. It's called reductio ad absurdum, right? Reductio ad absurdum, which is Latin for reduced to the absurd. The idea is I can assume something, usually something that your opponent is arguing for, right? And if I can show you that the assumption of that thing leads to something ridiculous or absurd, or more formally, contradictory, then I know that my assumption must be false. That's what we're trying to do with negation introduction. I'm trying to assume something to prove that it has to be false. Okay? Okay, we can use this to prove the law of non-contradiction. Remember, the law of non-contradiction looks like this. It's not the case that P and not P. Okay? We can prove this without any premises at all. That's why it's a law, all right? It doesn't require any premises. The way that looks is this. The premise bar is empty, right? There's nothing that we need here, nothing at all. We're going to start with an assumption, which is the opposite of what we're trying to prove. So this time, we're going to assume P and not P. Okay. Well, clearly, you can see there's going to be a contradiction, right? We can get P by itself using and a lim 1. We can get not P by itself using and a lim 1. This is going to lead to a contradiction. Negation elimination, 3, 2. And finally, that means it's not the case that P and not P. Negation introduction, 1 through 4. Okay. Now, technically, because we didn't have any premises, you don't even need this bar, which means this is a theorem. Okay. It's a theorem because it doesn't require any premises at all. Look how at the end here, there is no vertical bar. It's not an assumption. It's a truth, right? I've proved that something is true. Okay. Now, why is it that we can prove that this is true, right? Isn't this supposed to be deduction? It's because the system is built with this law in place. So it's a feature of the system. There are some philosophers who argue as to whether or not this is true, right? Some reject the law of non-contradiction, okay? Especially if you're working in something like quantum logic or something like that. But for our purposes, the law of non-contradiction cannot be violated. That's why negation introduction works. Okay, so that's negation introduction. Okay, we have 2 rules left. So the next is called indirect proof. Okay. Indirect proof. It functions basically exactly like negation introduction works, except for the fact that it doesn't introduce a negation symbol. And so it's often used to transform something that's what we call double negated into a non-negated expression. So something like this, not P, we can transform into P. These two things are equivalent, right? It's not the case that it's not the case that P is the same thing as P. Since a negation symbol just flips the truth value of whatever it's applied to, you flip something twice, well, it becomes what it was originally. How do we prove it? Looks like this. We have one premise, not P. We are going to start with an assumption of the opposite of what we're trying to prove. Again, same way as with negation introduction. This time I'm assuming not P. It will not P and not P are opposites, so I can draw a contradiction. That is going to be negation elimination, 1, 2. And from that, I can, instead of using negation introduction, just say P. No negation symbol at all this time. Indirect proof, 2 through 3. So it works exactly like negation introduction. It's just not negation introduction because we aren't introducing a negation symbol. That's it, right? It is literally the same thing, but we're not introducing a negation symbol. You are still going to assume the opposite of what you want to prove, show that that assumption leads you somewhere down the line to a contradiction, and then show that your assumption was false. Okay? So it's the same move conceptually. We just have to symbolize it differently because we're not introducing a negation symbol. Okay. Now, we have one last move, and it's pretty cool. It's called explosion. We symbolize explosion with an X. Indirect proof is IP. Now that's going to make this confusing with the contradiction symbol. There we go. Okay. So explosion, let's give an example and talk about how it works. Say you have this argument. If P, then Q and not P. You also know P and R. And the conclusion is A. Well, how are we going to get to A when it doesn't appear anywhere in the premises, not even close? It's going to look something like this. Set it up the same way as always. Okay. If P, then Q and not P. P and R. 1, 2. First step, I'm going to get P by itself. That's conditional elimination from line 2. Next step, I'm going to get Q and not P. That's going to be conditional elimination, 1, 3. Next step, I'm going to get not P by itself. Once again, that's conjunction elimination from line 4. And now I have a contradiction, right? Not P and P are contradictory, so I can use negation elimination, 5 and 3. But I'm not under any kind of assumption, right? My premises themselves seem to have this contradiction in it. So there's not really a way for me to get out by using like indirect proof or by using negation introduction. I just have a contradiction. Well, when you have a contradiction, you're always allowed to transform it into literally anything, like magic, right? It explodes into anything. So I can say A, explosion 6. Okay? Here's why this works. Because a contradiction is literally a violation of the laws of logic, if you are demanding that a contradiction be true, for instance, by placing one in your premises, then all the rules are off. Anything follows, right? You can say whatever you want at that point because you have virtually said the rules don't matter anymore. So, whenever you encounter a contradiction, you can explode it into anything you want. Okay? Now, sometimes students get confused into thinking that, well, if I can just use explosion, I don't really need something like negation introduction. That's not true. Okay, so if you have a standard negation introduction proof like this one, P then Q and not Q. Let's draw our lines. We're trying to derive not P, of course. You start with your assumption of P. This can get you Q through conditional elimination 1, 3. And of course, there's a contradiction now. Negation elimination 2 and 4. Couldn't I just explode to get not P? Why do I need why do I need all the other rules if explosion works? Can't I just do this? From 5. You always cite the contradiction symbol. No. The reason why is because you're still under this assumption. If you explode, you're still under the assumption of P. Okay? So explosion is very useful, but only if you're going to remain under that same level of assumption, right? It's not for this purpose. In order to get this not P out of the assumption of P, you must use negation introduction, right? That's the only way you're going to get out. Explosion does not end subproofs. Okay, so those are all of our rules. You now know, or you have seen all of them. Let's practice now a few of the problems from the book. So I am looking at the end of chapter 16. I'm looking at section C, where there are 12 different problems. And I am going to just kind of pick and choose from amongst them based on what I think looks good. So let's start with problem 7. Okay. Problem 7 says there are two premises. If it's not the case that F, then G. Second premise is if F, then H. And the conclusion is G or H. Okay, so let's solve this together. Step 1, let's draw our lines. I think the ones in this final section at the end of 16 are a bit trickier. So if you don't get it immediately, don't worry. Just keep practicing. These solutions can also be found on the ForAllX website. Not F, then G, and if F, then H. That's 1 and 2. Okay, so we're trying to get to G or H. How on earth are we going to do that? Well, we don't have G or H presently, but I do notice that if not F is true, I'm going to get to G. And if F is true, I'm going to get to H. And if I can get either one of those, I can use disjunction introduction to get my conclusion. Okay? So I really just need one of those, which means I need F or not F. Well, as it happens, that is the law of excluded middle, right? P or not P is the law of excluded middle. And the law of excluded middle is always valid, no matter what. So I know I must be able to prove that. It must be possible to prove F or not F, okay? So how am I going to do that? Well, I'm going to start by assuming it's opposite. I'm going to start by assuming it's not the case that F or not F. Okay. Now that I've assumed it's not the case, I'm going to assume, let's say, F. Right? This is another assumption. Okay. Now that I've assumed F, I can use disjunction introduction here to get F or not F. Remember, disjunction introduction says you can add a disjunction symbol plus anything else you want to something you know or have assumed. So this is from 4. But that's contradictory with the assumption I made on line 3. So I get to say, oh, I ran into a contradiction here. Negation, elimination, 3, 5. Since I ran into a contradiction, I'm allowed to say, my assumption of F was wrong. That's negation introduction, 4 through 6. Notice I'm still under my original assumption here. Okay? So I have not F now. Great. Well, what can I do with that? I can do the same thing. I can get F or not F, disjunction introduction from line 7. So another note about disjunction introduction, it doesn't matter which side you place your known information on. If you know P, you can get Q or P using disjunction introduction. It's the same move. Okay. All right. Now that I have F or not F, I've once again gotten to that contradiction. That's negation elimination, this time 3, 8. Okay, now that I've gotten to the contradiction again, I'm going to use indirect proof to prove that F or not F. That's going to be indirect proof 3 through 9. Whew, I proved F or not F. Am I done? No, unfortunately, I am not done. There's still quite a bit more work to be done, okay? Still quite a bit more to do. Now, I have to prove that both sides are going to lead me to G or H, right? That's my goal. So now I'm going to need to make more assumptions. I need to try to eliminate this disjunction. So I'm going to begin that by assuming the left side first. That's F. Show that F leads me, oh, looks like it leads me to H. These lines need to be longer. This is going to be somewhat of a long proof here. Okay. Now that I have H, I can get G or H. Oh, I need to cite a step here. That's conditional elimination 2 and 11. I can get G or H using disjunction introduction, line 12. And that's my conclusion. So I can move on now to my next subproof, assuming the right side of my disjunction on line 10. That's not F. Right? Assuming not F, I can get to G using conditional elimination. That's 1, 14. That can also be turned into G or H using disjunction introduction over line 15. And finally, on line 17, I can say G or H, disjunction elimination from line 10, 11 through 13, 14 through 16. So, quite a long proof at the end. Okay? There will be some additional rules we learn later on that will make this much simpler. For example, if we could have just stated that F or not F, which we will be able to do in a manner of speaking later, that would have saved us 10 steps, right? But this is a complete proof. This is valid. Now, maybe you approach this slightly differently. That's okay. Maybe, for instance, you assumed or you started with the assumption that G or H is false in an attempt to do some sort of negation introduction proof. That's fine. So long as you only use valid inference rules and you arrive at the correct result, it's a good proof. No two proofs have to look the same in order to both be good proofs, right? Some proofs might be more elegant in that they take fewer steps. That doesn't make them any more correct. Okay, now let's look at problem number 10. Problem 10. Problem 10 says S if and only if T, and the conclusion is S if and only if T or S. This one's going to be a bit simpler. Start the same way as always. We only have one premise this time. S if and only if T. Okay, now notice our conclusion is a biconditional. We are trying to introduce a new biconditional, and there's only one way to do that, using biconditional introduction. That requires two subproofs. The first subproof starts with an assumption of the left side of the biconditional we're trying to introduce. So let's start with S. And we are trying, of course, to arrive at the right side after that assumption, T or S. So can we get to T or S? Certainly. We get T using biconditional elimination, 1, 2. We can get T or S using disjunction introduction, line 3. Okay. Next up, our second subproof. We're going to assume the right side and try to get to the left side. So let's assume T or S. This is going to get a bit messy, so let's get our second bar a little more. Let's get it a bit cleaner. Okay. T or S. Now notice this is a disjunction. And as I said earlier, disjunctions are generally not that useful in a proof unless you use disjunction elimination, which is what we're going to have to do. That's going to require two more subproofs within this subproof. Okay? We're going to start with an assumption of the left side, T. Can T lead us to S? Well, certainly. We get that with biconditional elimination. 1, 6. Great. Now we want to show that assuming S, which is, of course, the right side of this disjunction, also leads us to S. Okay, well, That's pretty clear, right? Because S is S. This is our often underused rule, reiteration. Line 8, we're just repeating ourselves. On line 10, we get to say, so I'm allowed to eliminate my disjunction that I found on line 5 because of subproofs 6 through 7 and 8 through 9. Now I have shown that assuming T or S leads me to S. Great, that's exactly what I was looking for. So on line 11, I can come out and say S if and only if T or S. Biconditional introduction 2 through 4, 5 through 10. Okay? Bit simpler than the last one, but still a bit involved given that it has multiple nested subproofs. Okay. Let's see. How about we do one more? Let's look at problem number 12. Let's see. Problem number 12 says it's not the case that P then Q. And the conclusion is P. So let's set it up the same way as always. Premise 1, it's not the case that if P, then Q. And we're trying to arrive at P. Okay, so we're trying to arrive at P. That means if you have something like this, your conclusion is just a single sentence letter, and there's no immediate way to derive it, like there's no conjunction that you can eliminate or something like that. There's no modus ponens or conditional elimination to use to get it out of there. You're probably going to want to start by assuming its opposite. So let's start by assuming not P. Now, not P doesn't really get us anything. We're just hoping that we can assume something else that's going to generate a contradiction for it. Okay? So our next move is going to need to be another kind of assumption, right? Going to need to be yet another kind of assumption. What if we assumed, let's think. What should we assume here? If we assume P, we can get Q, but that doesn't help us. It would if we made it into conditional. Okay, so what if we did something like this? Let's assume P. Okay. Now, we want a conditional. So the reason why I'm saying we want a conditional is because we're trying to generate something that contradicts with this, with line 1. And the only thing that would is a conditional that says this, if P then Q, okay? So we need to show that by assuming P now, we can get that. We can get a contradiction later down the road. And the only way to do that is going to be to draw a contradiction right now. Negation, elimination, 2, 3. And from a contradiction, anything follows like Q. That's explosion from line 4. Let's shorten this up. Now, if you remember our conditional rules, I'm entitled to say if P then Q, conditional introduction 3 through 5. But look, that's contradictory with premise 1. Contradiction, negation, elimination, 1, 6. Okay. bring this up here. Line 8, I now get to use my indirect proof move. I get to say P must be the case using indirect proof 2 through 7. Why? Because my assumption of not P led me to a contradiction. So I know it must be false. Okay? This one's a bit tricky. This one is it's not as easy without practice to see what the proof strategy ought to be. Particularly this move is not something I would expect a beginning student to be able to see very quickly. Okay, so again, if your conclusion or whatever you're trying to arrive at does not appear in the premises in such a way that you can get it out, either by conditional elimination, biconditional elimination, some kind of complicated disjunction elimination proof, etc., you're probably going to want to assume it's opposite. Okay, so in this case, it was not P. From there, you might get in a situation where you still don't know what to do. If that happens, start making assumptions that have a good chance of leading you towards generating a contradiction. Just keep in mind that any assumption you make, you're going to have to terminate. You cannot end a proof in natural deduction with hanging assumptions. Right? They all have to be ended by the time you finish the proof. Okay, so there's a lot more to practice. This kind of thing, you really only learn with practice. So I encourage you to look at the problems in the back of the book, the solutions, etc. Okay, so next time we're going to learn a few rules that are going to make life a lot simpler. Modus tollens, the ability to cite the law of excluded middle, for example, right? Instead of having to use those 10 steps. So we'll learn those kind of rules next time. Until then, practice with these. Check out the problems in the book. See if you can solve them. All right. But that's it for this time. So see you next week.